friends, today we are going to learn very important topic of organic chemistry under hydrocarbons, alkynes.
As we know, under hydrocarbons we have learned that hydrocarbons are broadly divided into two types. What are they? Aliphatic and aromatic, isn't it? Aromatic. Aliphatic, saturated, unsaturated. Saturated and unsaturated. Under unsaturated, yes, we will have alkenes and alkynes So alkynes are the compounds of hydrocarbons having unsaturated hydrocarbons. So what is the general formula for these alkynes? Yes, CN H2N minus 2. What about alkenes? Yes, it is CN H2N. What is this? CN H2N plus 2. Yes friends. So under these saturated alkanes are the saturated hydrocarbons. Alkenes are unsaturated hydrocarbons. Alkynes are the compounds having unsaturated carbon. So alkanes will have sp3 hybridization. Alkenes will have sp2 hybridization. Alkynes, what is hybridization? sp hybridization, isn't it? sp hybridization. For example, alkanes, methane, CH3, ethane. This is ethane, right? Under alkenes, C double bond CH2, ethylene. Under this sp, the first compound under alkynes is acetylene, C triple bond H and H. This is acetylene. Our IUPAC name is ethyne or acetylene. Common name is acetylene. Ethyne or acetylene. Ethane, ethylene, ethyne. So these are the alkynes. Today we are going to learn about alkynes, their preparation and their chemical properties. Alkynes will have sp hybridization. Yes, what is the molecule? Acetylene. Let us take acetylene, C single triple bond. This is acetylene. In acetylene we have sp hybridization. This is the sp hybridization. So how it is going to take place? We know that yes, this is one p orbital. This is one p orbital. Yes. So these are sp hybridized orbitals. Another orbital is pxy and pxx. So we have, this is sp hybridized molecule. So this hydrogen is going to form like this. Yes friends. So this is how hydrogen is going to form this. Right. So this is hydrogen. This is one carbon. This is hydrogen. This is one carbon. Yes friends. So let us understand. I am drawing first. So this is the bond and this is the bond and this is the bond. So this is sp hybridization. sp hybridization found in sp hybridization takes place in acetylenes, right? So in sp hybridization we will have one sigma bond. This is sigma bond. End on end overlapping of 2pz orbitals of carbon takes place to give sigma bond. So this is one sp sigma bond, right? So this is one pi bond. This is another pi bond where 2px of carbon and 2py of carbon takes place. 2px and 2py of another carbon. Dear friends, in acetylenes we will have one sigma bond, two pi bonds between carbon plus what is this? Hydrogen. It is also one sigma. So each carbon will have one sigma plus one sigma, two sigma bonds plus two pi bonds. So two sigma bonds, it is going to have two sigma bonds means sp hybridization. sp hybridization takes place between these acetylenes. Acetylenes will have sp hybridization. Since it is sp hybridized molecule, the structure of this sp hybridization is linear. The shape is linear. And what is the bond angle between these two carbons? So it is linear, 180 degrees. Right friends? Since it is a triple bond, it is strongly very near to each other, closely. They are intact. So bond length in C triple bond C is what is the bond length? Yes, 1.20 angstroms or 120 picometers. Yes friends, so angstroms are 120 picometers, right friends? So this is shorter than C double bond C. What is the bond length? Yes, we know 1.33 angstroms or 133 picometers. At the same time, it is also shorter than CC single bond. What is the bond length? What is the bond length of CC single bond? It is 1.54 angstroms or 1.154 picometers. So the bond length of this C triple bond C is shorter than C double bond C and C single bond C. Yes friends, since it is shorter, so it is tightly packed or closely packed. So to break this bond, we need some energy. That energy is known as bond strength or bond strength. The name of bond strength is also known as enthalpy, right? So enthalpy of CC triple bond is more than C double bond C and C single bond C. What is the enthalpy of this? So enthalpy of CC triple bond is known as bond enthalpy. For CC triple bond, it is 823 kilojoules per mole. Yes friends. So whereas to CC double bond, it is 681 kilojoules, whereas this is 348 kilojoules per mole, and it is kilojoules per mole. Dear friends, these are all very important while understanding the reaction mechanism while writing. So this is CC triple bond sp hybridization. It is having how many sigma bonds? It is 1 sigma bond. Here it is 1 sigma bond. Here it is 1 sigma bond. Whereas these two are pi bonds, right? So acetylene, it is acetylene sp hybridization, right friends? So this is how sp hybridization takes place in alkynes. So these are the alkynes having sp hybridization and CC triple bond compounds. So it is bond, yes, these are linear molecules and bond length is shorter than alkenes and alkanes, whereas bond strength is more to alkynes, that is 823 kilojoules per mole for alkynes, whereas to alkenes it is 681, for alkanes it is 348 kilojoules per mole. Yes friends, this is how general introduction of alkynes. Yes, so the this is sp hybridization. It is very important friends, how it is packed. So based on this, so sp hybridization, we are going to learn some properties of alkynes of CH. This is the bond, it is loosely attached compared to alkenes and alkynes, so that it easily liberates or it easily gives out H plus ions. So it acts as weakly acidic. It acts weakly acidic compound. Alkynes are weakly acidic compounds. So if you know the structure, then only you can understand how or why it is going to act as acidic. Right friends, this is how sp hybridization takes place in alkynes. Next, let us see the nomenclature and what are the compounds, how to write the compounds names. Yes, common names of alkynes, for examples, what I said, CnH2n-2 is alkyne molecular formula. General molecular formula of alkynes is CnH2n-2. If n equal to 2, what is the compound? C2H2. It is nothing but, yes, I can write CH triple bond. This is common name of this compound is acetylene. IUPAC name is what is the IUPAC name? It is ethine. It is ethine. Right friends? If it is n equal to 3, what I am going to get? C3. 3 to the 6 minus 2. It is 4. Right friends? So what I am going to get is CH3, C triple bond CH. This is methyl acetylene. Methyl acetylene. It is common name of alkynes and IUPAC names. Yes friends. So acetylene, methyl acetylene, or IUPAC name is propyne. Dear friends, So as we know, it is alkanes, we call it as ethane, ane for alkanes, ene for alkenes. So for alkynes we use ine. So this is how we can ethane, ethene, ethyne, IUPAC name. So propane, propene, propyne. So methyl acetylene. When N equal to 4, C4, 4 to the 8 minus 2 is 6, H6. Right friends? So it can be CH3, CH2, C triple bond CH. So ethyl acetylene, common name is ethyl acetylene. Right? So what is the name of IUPAC? But 1 ine. It can have another structure, same molecular formula, CH3, C triple bond C, CH3. 1, 2, 3, 4, 4 carbons, 3, 3, 6, 6 hydrogens. So same carbon, same molecular formula. So these two are isomers, right? Ethyl acetylene, and this is 1, 2 dimethyl acetylene. So common name of this is 1, 2 dimethyl acetylene. So IUPAC name is but 2-ine. But 2-ine. This is how you can nomenclate or give the name of these compounds. So these two compounds are nothing but positional isomers. Positional isomers. So these two are position isomers. Let us take N equal to 5. Let us try N equal to 5. How many structures do you expect? Yes. So C5H8. Right friends? So let us write common name CH3, CH2, CH2, C triple bond CH. Right? Propyl acetylene. Yes, propyl acetylene. No problem. Propyl acetylene. You can write propyl acetylene. When it is propyl acetylene, common name is so pent 1-ine. Pent 1-ine, 5 carbons. It can have another structure CH3, CH2, C triple bond C, CH3. Same number of hydrogens, same number of carbons. So it is pent 2-ine. This is pent 2-ine. Right friends? So it can have another structure. What is the another structure? CH, CH3. Right friends? CH, C triple bond CH. 1, 2, 3, 4, 5 carbons. Hydrogens 3 plus 3. Right? 6, 7, 8. So this is methyl. 1, 2, 3. 3 methyl. Right? But 1-ine. But 1-ine. Isn't it? 3 methyl. But 1-ine. So these three compounds are all are isomers. So these two are position isomers. Right? Position isomers. When it comes to, since the triple bond is position only change, these two compounds, what is the change? The triple bond position, it is 1, here it is 2. So when it comes to any of these two, let us take with these and these and these. What is this? Chain isomers. So this is chain isomers. I will explain in isomerism in detail about what is position isomers and chain isomers. So here just learn these two are chain isomers or these are isomers. So since triple bond can exist anywhere in a chain or homolog, so based on the position of the triple bond we can give a name pent 1-ine, right? Pent 2-ine. Wherever the triple bond is there, give the number of that place and at the end write ine. Right friends? So as per IUPAC name you can write like this. So if you try when it is N equal to 6, let us see. So if you want to write down, you can write on your own or for your understanding I am going to solve it also. So when N equal to 6, right? What is the molecular formula? C6, H12 means H10, right? So let us write the structure. What is the structure? So what is the isomer? CH3, CH2, 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 C triple bond CH. Right friends? 1, 2, 3, 4, 5, 6. 6 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is This is hex 1 ine. Any confusion? No. Or I can write the same compound CH3, CH2, CH2, C triple bond, C, CH3, hex 2 ine. This way you can go and write different types of compounds with same molecular formula. These are all isomers, right friends? So I can write another compound CH3, CH2, C triple bond C, CH2, CH3. So this is X 3 ine, right friends? So these three are 1, 2, 3. The position of triple bond is at 1, 2, 3. So if I put here, it again becomes X2N. If I put here, it again becomes X1N. So what are the other isomers are possible? So I can write the same molecular formula compound in a different way. I can write this way also. CH3, CH2, CH2, C triple bond CH. Here I can write methyl. How many carbons are there? 5 plus 6. 1, 2, 3, 4, 5, 6. Right? So hydrogens are matching 3, 2, 5, 6, 7, 8, 9, 10. Right. So what is the compound? It is 1, 2, 3. 3 methyl pent 1 ine. Right. So the same compound I can write in this way also. CH2, CH, CH3, CH2 and C triple bond CH. So here 1, 2, 3, 4, 4 methyl pent 1 ine. So this way you can write down different ways, right friends? So EF, let us change the double bond position. CH3, CH2, triple bond CH3, 1, 2, 3, 4, 5. So let us write here methyl group. So what is going to happen? 1, 2, 3, 4, right? So 4 methyl pent 2 ine, isn't it? So 4 methyl pent 2 ine. So another way, how can I write? Yes, another way, yes, it is possible to write even this structure. So what is the structure? CH3, C, CH3, CH3, C triple bond CH. Yes friends. So 1, 2, 3, 3 dimethyl, 3 dimethyl, 1, 2, 3, 4 but 1 ine. So these are all the isomers possible for n equal to 6. You can try number of isomers taking n equal to 7, 8, 9, 10. So this is how you can expect different structures for when it is n equal to 6. These are all isomers friends. So this is all about alkynes. Acetylene, methyl acetylene, the common name is propyne, butane, pentane, hexane, like that. All alkynes, right friends? So let us learn the preparation of alkynes. Method 1 is, let us take one compound, gem dihalides. This is gem dihalide compound. It is nothing but, what is this? 1,1 dichloro ethane. So this is gem dihalide, dichloro, dehydrohalogenation of gem dihalides. So upon using KOH, elimination takes place of this HCl to give this is a compound hydrogen. Yes, hydrogen will be here, double bond C, chlorine will be there, hydrogen, and this further loses HCl, this HCl in presence of sodium amide to give acetylene. This is acetylene compound. This is one of the methods known for the preparation of alkynes. Acetylene, right friends? So this is acetylene, right? Next, another method is, yes, same, this is dichloro. Let us take vicinal dihalides. Let us take hydrogen. Here I am going to take bromo. This is vicinal dihalide. It is nothing but vicinal. 1, 2 dibromo ethane. 1,2-dibromoethene upon KOH. Yes, using KOH under heating conditions, it is going to lose this HBr, right? So this HBr is going to be loosed to give this is the compound, hydrogen will be there, double bond, C bromide, right? Hydrogen will be there. So this further similar to this reaction, it is going to lose further amide and going to give acetylene. Same compound we are going to get. Another method, dehalogenation method, tetrahalo compounds. Tetrahalo compounds. Tetrahalo, let us take, this is bromo, this is bromo, this is bromo, this is bromo, hydrogen and hydrogen. 1122, 1122, tetrabromo, tetrabromo, ethane. Now, since it is tetrabromo, let us use zinc. Yes, so zinc loses these tetrabromide as -2 zinc bromides to give acetylene. So first method is dehydrohalogenation of gem dihalides or vicinal dihalides, dehydrohalogenation of vicinal dihalides. And third method is tetrahalo compounds upon dehalogenation using zinc. We are going to get alkynes. Another method, let us see. Another method is electrolysis of, yes, Kolbe's electrolysis. Electrolysis method. We are going to get alkyne. How? Let us take malic acid, potassium salt. Malic acid, potassium salt upon electrolysis, cold electrolysis. We are going to get acetylene. Potassium malleate. So instead of malleate, yes, even if I take fumaric acid, what is fumaric acid? Yes, it is trans potassium salt. Yes, trans acid is potassium salt of fumaric acid. Upon Kolbe's electrolysis, we are going to give acetylene. Acetylene can be prepared by Kolbe's electrolysis. Let us take another mix, carbides. So preparation of alkynes from carbides. Let us take calcium carbide. Calcium carbide can be prepared from calcium carbonate upon, yes, heating. We are going to get calcium oxide plus carbon dioxide. This calcium oxide upon heating with carbon, yes, this calcium oxide upon heating with carbon, we are going to get calcium carbide plus this is CO, right? Calcium carbide, this is calcium carbide. It is very important to make our acetylene compound. Calcium carbide, this calcium carbide upon hydrolysis, yes, H2O, it is going to give C2H2. It is acetylene plus calcium hydroxide taken twice. So this is how acetylene can be prepared from calcium carbide. This calcium carbide can be obtained from calcium oxide. This calcium oxide usually obtained from limestone. This is calcium carbonate is a limestone. This limestone gives quicklime. This is quicklime. This quicklime gives calcium carbide. Calcium carbide gives acetylene upon hydrolysis. This is one of the methods. Yes. Or instead of calcium carbide, magnesium carbide also can be used. Magnesium carbide. So magnesium carbide can be used. H2O, we are going to get propine. This is propine, CH plus magnesium hydroxide taken twice. This is 4H2O, 2 magnesium. So magnesium carbide gives propine. This is propine. It is an alkyne. Propine we are going to get from magnesium carbide. Carbides upon hydrolysis we are going to get these acetylene compounds are alkynes. Yes, we can prepare deuterated compounds also. For example, if I treat this calcium carbide with 2 moles of deuterium oxide. Deuterium oxide, what is the compound I am going to get? C2D2. This is deuterated acetylene. Deuterated acetylene plus calcium OD. This is I am going to get calcium hydroxide, that is deuterated hydroxide I am going to get, or deuterium oxide, right? C2D2 is deuterated deuterium oxide. So deuterated water I am using, I am going to get deuterated acetylene I will get, right? So same way, in a similar manner, if I use, instead of this water, if I use deuterated water, 4D2O, right? What I am going to get? 4D2O, CD3, C triple bond CD plus 2 magnesium OD taken twice. This is how deuterated propane I am going to get. So these are the methods for the preparation of alkynes. Dear friends, let us see the physical properties of alkynes. Physical properties of alkynes. First 3 members, that is from acetylene to C2 to C2, C3 and C4, these are gases, and C5 to C13, yes, these are liquids, and from C13 above C13 are solids. So when it comes to, so let us write C5, what is hydrogens? 8, so 13, 26 means 24, H24. So the compounds having the molecular formula of C2, H4, H2, acetylene to C4, H6, that is butane, up to butane, these are gases, and whereas from pentane to remaining are liquids, these are liquids, and above this C13H24 all are solids. So this is physical properties. When it comes to melting point, yes, so as the molecular weight increases, melting point also increases. Yes, as you know, alkynes are organic compounds immiscible with water, however miscible or soluble, miscible with organic compounds, organic solvents like CCl4, benzene, right? Or you can take ether, diethyl ether, like that. So these are soluble or miscible with organic solvents, whereas these are immiscible with water. So melting point increases as the molecular weight increases, since these are solids above C13. And colorless compounds, all are colorless compounds. And smell, when it comes smell, so odorless, there will be no odorless compounds. However, acetylene, yes, acetylene will have some specific smell. Acetylene will have specific smell, right? So this is, except acetylene, all are odorless, means no smell, right friends? So colorless, no smell, except acetylene. So all are gases up to pentane are gases, remaining from C5 to C13 are liquids, C13 above compounds are solids. As the molecular weight of these solids increases, the melting point also increases. As usual, liquids also molecular weight increases, boiling point also increases, right? So boiling point also increases. Alkynes are immiscible in water, whereas miscible with organic solvents like CCl4, benzene, diethyl ether, whatever solvents you try, right friends? So these are the physical properties to learn. Chemical properties of alkynes. Yes friends, since these compounds are having C triple bond in their structure, so these are unsaturated compounds, usually undergoes addition reaction takes place. Addition, especially electrophilic addition reactions will take place. So electrophilic addition, let us write electrophile and nucleophile. This is electrophile means positive charge, nucleophile means negative charge, right friends? So the electrophilic addition will take place in the first step to give S R C double bond. This is vinyl carbocation. So this electrophile will add Markovnikov, will follow Markovnikov's addition. Markovnikov's addition will take place. So addition will take place, Markovnikov's addition will take place where carbocation will be secondary carbocation. Right friends? This secondary carbocation further, yes, depending on its stability, either it isomerize or then it adds to nucleophile. So to give R, C, nucleophile, double bond, CH and electrophile. So this is the intermediate. At this stage it may stop or further it can undergo further addition since it is alkene. Yes, it can add another nucleophile or electrophile. So alkenes usually undergoes electrophilic addition. So this comes here to give R, C, already nucleophile is there, C, H, electrophile is there and another electrophile, this is another electrophile will come and sit here and here positive charge, right? Next nucleophile will come and sit here to give R, C, nucleophile, nucleophile, electrophile, electrophile and hydrogen. This is the common trend of electrophilic addition reactions. Electrophilic addition reactions. Right friends? So for your better understanding, if I take HBr, E equal to H and nucleophilic equal to Br. So what I am going to get? HBr, R, so Br dibromo, hydrogen will be there, hydrogen will be there. So this is the compound I am going to get in general. So the addition follows Markovnikov's addition. Markovnikov's addition reactions will take place. So addition reactions, the number one is addition reactions. So another type of reactions is oxidation reactions. It undergoes oxidation reaction, right? So under addition reaction we will learn about hydrogen halide or acid addition, so halogen addition, water addition, B2 diborane addition, arsenic chloride addition. So like this we will learn in detail about these addition reactions. Next oxidation with KMnO4, right? Alkaline KMnO4. We will learn about ozonolysis, and these compounds also undergoes polymerization. Very important reactions of alkynes are polymerization reactions. And the Diels-Alder reaction. Diels-Alder reaction. It is also very important reactions of alkynes. Diels-Alder reactions. So this is how alkynes usually undergoes addition reactions, oxidation, polymerization and Diels-Alder reactions. Let us learn in one by one. Right friends? So this is the common trend of electrophilic addition where electrophile adds first followed by nucleophile. Then since it is going to give alkene type compound, this alkene further undergoes electrophilic addition reaction with another molecule of the reagent with same electrophilic addition type reaction to give so di compound. For example, if I take HBr, where we are going to learn HBr, so we are going to get this dihalo compounds, gem dihalo compounds. So this is how we are going to get the compounds. Let us learn in detail about one by one. Or this is also known as reduction of alkynes, right? Or reduction of alkynes where triple bond is going to reduce to double bond or single bond. For example, if I take, what is this? But-2-ine. So read like this, not but-2-ine. But-2-ine, butane, not but-2-ine, but-2-ine. So upon reduction using hydrogen, palladium over carbon, instead of palladium I can use platinum or nickel. So usually we use palladium carbon in organic chemistry. So I am going to write palladium carbon to give CH3, CH2, CH2 and CH3. So it is butane. So since it is catalyst, it is metal catalyzed hydrogenation. So the hydrogens will attack from same side. Free radical addition takes place. Free radical addition takes place. So if you think this is the metal surface, this is the metal surface of palladium. So hydrogens are attached like this. So these hydrogens slowly approaches to this side. and it is a linear molecule. Immediately this side another molecule of hydrogen also comes and cis addition takes place, cis addition. So syn addition, we call it as syn addition to give this butane, right friends? So free radical addition, syn addition takes place. So this is free radical addition takes place. Alkyne gives alkanes. Alkyne gives alkane. However, under partial reduction means if I add the poison like barium sulfate, since it is having sulfur is going to act as poison. Sulfur is going to act as poison in palladium, poison for palladium catalyst. So it stops at certain stage to give, if I take the same butane CH3, C triple bond C CH3, so I am going to take hydrogen, right? So palladium on carbon, I am adding barium sulfate. Which is going to act as poison. This will stop at certain stage, that is partial reduction takes place to give CH3. So these two hydrogens are, since I said it is going to add from the same side, so in this reaction we are using palladium. So what is the alkene? What is the geometry of this alkene? Cis butene. So this is cis geometry. Two methyl groups are at same side. So cis geometry, cis to each other, cis geometry. This reaction is known as Lindlar catalyst. This catalyst is known as Lindlar catalyst. So when we add Lindlar catalyst, we are going to get cis alkene. This is very important point in organic chemistry. So Lindlar catalyst gives cis hydrogenation or cis alkenes. So what is the opposite of this? Yes, we do have opposite reaction to this also. If I use the same compound, if I use sodium in liquid ammonia, hydrogen, right? Sodium in liquid ammonia, I am going to get trans alkene. So this is different mechanism where I am going to get trans alkene. So this is trans alkene, trans butene. So what is the name of this reaction? This reaction is Birch reduction. Very important friends. Birch reduction gives trans butene, whereas Lindlar reduction gives cis butene. This is how addition of hydrogen takes place. Halogen. So let us take bromine. So I am taking acetylene. Upon bromination, Br, I can write like this, Br. Usually we will take it in CCl4. So what is going to happen? It can have partial positive and partial negative, right? So it is going to give, this is a compound. I am going to write with mechanism hydrogen. So I am going to attack here, right? So this is the intermediate, and this further, since it is going to have this bromine minus, it comes and sits here to give C, bromine, double bond, CH and bromine, right? So I have taken only one mole. If I use one more mole, bromine and bromine, this is alkene. Alkenes also undergoes addition reactions. So I can write partial positive and partial negative. It takes up this bromine to give bromine is here, right? So here it is going to have positive charge, hydrogen. Already bromine is here, new bromine has come, right? This further takes up another bromine which is there in the reaction mixture to give tetrabromo compound C, H, bromine, 1, 1, 2, 2, tetra, bromo, ethane, right friends? So if I want, I can stop here also. Dibromo compound also I can isolate. So if I use only 1 mole of bromine, I can stop at this stage to get 1,2-dibromo ethene, right? Ethylene I can take 1,2-dibromo ethylene also. If I use directly right? I can use directly 2 moles of bromine. If I use 2 moles of bromine, I will straight away I will get this tetrabromoethane. This is how bromination takes place. Bromination takes place. Addition of halogen, bromine. Right friends? Bromine I have taken. Next. So let us take simple example. RCCH. So let us take HCl. H plus Cl minus. What I said, electrophilic addition takes place to give R, C, double bond, H. This is a positive charge, right friends? So next this going to attack here to give R, C, chlorine, C, hydrogen, right friends? So this is the compound I am going to get, vinyl chloride, right? So this further addition to another molecule of HCl, right, H plus Cl minus, it is going to give, right, R, C, L, hydrogen, and this is positive charge. Next it attacks here to give R, C, Cl, hydrogen, and hydrogen. So this is how it follows Markovnikov's rule. So let us take one more example, specific example. I will ask a question, right? C, triple bond, CH. So what is the compound? Are you going to get CS3, C, hydrogen, C, chlorine, hydrogen? Are you going to get this 1,1-dichloropropane? 1,1-dichloropropane. Are you going to get this? Or CS3, chlorine, hydrogen, and hydrogen. Or 2,2-dichloropropane. So what compound are you going to get? This is A, this is B. I am going to react with same HCl excess, or I can write 2 moles of HCl. So am I going to A or B? Let us see. Just think. So since it is electrophilic addition reaction, HCl, it attacks first this hydrogen, right friends? It is going to give CH3, C, double bond, CH. If I write here hydrogen, so what is the carbocation here? Vinylic. However, it is secondary carbocation. So if this hydrogen adds here, CH3, hydrogen, double bond, hydrogen, carbocation. This is, what is the carbocation? Primary carbocation. Among primary and secondary, which is more stable? Carbocation stability. Secondary carbocation is more stable than primary carbocation. This is very, very important, friends. It's just, if you remember this stability of carbocations, just go and add. You will get the compounds. Yes. So now what happens? It is going to attack chlorine. It is very simple, right? Chlorine. It is going to give CH3, chlorine, double bond will be there, hydrogen and hydrogen, right? Now it is going to attack with another chlorine molecule, H plus Cl minus. Again same question, right? Since it is an alkene, alkenes follows Markovnikov's addition reaction. CH3, C, already chlorine is there, right? So it is going to give this positive charge, hydrogen and hydrogen, new hydrogen, this hydrogen comes and sits here. So this is CH3 has become. Now instead of this, if I write hydrogen here and here, so what is the carbocation? Again I am going to get primary carbocation. This is secondary carbocation, more stable. So this carbocation adds to chlorine, right, to give dichloro, 2,2-dichloro compound, but not 1,1-dichloro. Yes friends, so it is going to give this 2,2-dichloro compound. Addition of hydrogen halide gives 2,2-dichloro compounds. So it follows Markovnikov's addition. Next, are going to react with water. Let us see. We use mercury sulfate in presence of dilute sulfuric acid, or you can write it as mercury 2 plus and H plus. This way also you will get. So an arrow mercury sulfate and sulfuric acid, dilute sulfuric acid we will use, or H plus some under acidic reaction mixtures. Let us take, for example, if I take this acetylene and I am going to react with HOH, I can write like this. Any problem? H plus OH minus. For your better understanding, I am writing like this. So it reacts with this and to give CH, right? So this is H plus, or new hydrogen has come. So this is the carbocation we are going to get intermediate, right friends? So this OH minus which is there in the reaction mixture, so what we are using, mercury sulfate and dilute H2SO4 to give this intermediate. This reacts with this water molecule to give hydrogen COH double bond CH. Yes, so this hydrogen is here, right friends? So this is the intermediate. So vinyl alcohol tautomerism to give aldehyde. So what happens? It goes here and comes here. This hydrogen comes here to give hydrogen, and here hydrogen. What is this? Acetaldehyde. So this is one alkyne. We can say one alkyne. This one alkyne, what we are going to get? Acetaldehyde. Acetylene, we are going to get acetaldehyde. Instead of acetylene, if I take propane, CH3, C, triple bond CH, and do the same reaction, HOH, I can write like this, mercury sulfate in presence of H plus, right? So what is going to happen? It is going to take up this. So again, here question comes, where this hydrogen has to come and sit. So the thumb rule is secondary carbocation. Just remember, this is secondary carbocation I am going to get, right? So secondary is more stable. So this is the intermediate I am going to get. Next, what happens? The minus OH which is there in the reaction mixture comes and sits here to give. This is the intermediate CH3, COH and CH, and this is a double bond, right friends? Now what happens? It tautomerizes. Tautomerism. So enol to ketoenol, tautomerism. So this is ketoenol tautomerism. So upon ketoenol tautomerism, it turns into ketone. It gives rise to ketone. C double bond O CH3, right? Here CH3. This is acetone. It is nothing but ketone. So ketone, this is enol. This is also enol. Ketoenol tautomerism gives ketones. So this is very, very important friends. It is not going to give this CH3, C, CH2 and double bond H. This is propionaldehyde. This is not going to give this propionaldehyde, right? Because it follows this Markovnikov's addition rule to give ketone, right friends? So here also Markovnikov's addition, it gives acetylene gives aldehyde, and remaining, yes, other than acetylene are going to give ketones. Yes friends, this is how addition of water takes place to alkynes. Next, alcohol, right? So take common example C, triple bond CH. I am going to react with methanol. I am going to take methanol, right? So methanol is compared to alkyne, it is going to be acidic. So it gives rise to plus and minus. It reacts with H plus ions to give RC double bond. Here positive charge, and here it is hydrogen and hydrogen. Now what is going to happen? OCH3 minus is going to attack here to give R OCH3 double bond hydrogen. What is this? If R equal to hydrogen, So what I'm going to get? Hydrogen OCH3 double bond C hydrogen and hydrogen. So this group is vinyl, this is methyl, methyl, vinyl. What is this? COC, ether, methyl vinyl ether, ether, methyl vinyl ether. I am going to get. So addition of alcohol to alkynes gives ethers, vinyl ethers, vinyl ethers we are going to get. Next, addition of carboxylic acid RCOOH, right? So what I am going to get? Let us take same R, C triple bond C, H, right? So I am going to take, for example, acetic acid OOH. So these acids usually gives H plus ions, easily gives H plus ions, right? So this H plus ion attacks on this to give R, C double bond carbocation, C hydrogen and hydrogen, CH3 CO O minus, right friends? So this comes and sits here. So this gives what? R C O C CH3, right? Double bond C hydrogen and hydrogen. Vinyl acetate, vinyl acetate. So if R equal to hydrogen, so what is the compound? Hydrogen C O O CH3 double bond CH and CH. So what is the compound here? This is acetate, this is vinyl, same vinyl is here. So vinyl acetate, vinyl acetate. I am going to get vinyl acetate. Addition of carboxylic acids gives, addition of carboxylic acids to alkynes gives vinyl acetate. Addition of alcohol gives vinyl ethers. So this is how addition of alcohol and acids takes place, right? So let us take acetylene, our starting compound acetylene, right, upon HCN, hydrogen cyanide, right? Reaction with hydrogen cyanide, H plus Cn minus, same mechanism, H double bond CH. Here I am going to write positive charge, and the cyanide, what is going to attack here? I am going to get H cyanide double bond CH and CH. Acrylonitrile, acrylonitrile, it is very important synthetic intermediate in organic chemistry. Acrylonitrile can be prepared from acetylene, can be prepared from acetylene, right friends? Addition of arsenic trichloride. If I take same acetylene, C triple bond C hydrogen and arsenic trichloride, so it attacks here hydrogen C chlorine double bond C hydrogen and arsenic chloride. So this is known as Lewisite. Lewisite. It is a poisonous gas. Poisonous gas. So Lewisite can be prepared from acetylene by reacting with arsenic trichloride. Yes friends. Next, hypohaous acid. Halous acid, for example HOCl, right? So this is very peculiar reaction. For example, if I take acetylene, right? So in this reagent, chlorine is going to act as electrophile. This is going to act as nucleophile, right friends? So first chlorine will be added to this to give double bond, right? So C hydrogen is there, chlorine is there. Next OH minus will attack here. It is going to attack here to give OH, right? Double bond CH chlorine, right? So here it may not stop. If it stops, yes, it gives this ketoenol tautomerism. Yes, it will give aldehyde here itself. So you will get very little amount of this. Hydrogen will be there, but it adds to another molecule of HOCl, right? HOCl to give Cl plus minus. So here addition of electrophilic addition takes place. This is hydrogen COH, right? So C single bond hydrogen, chlorine is here, second chlorine, second chlorine is going to attack here, right? So here positive charge, next OH minus which is there in the reaction mixture come and attack here to give COH, COH, single bond, chloro, chloro, hydrogen, hydrogen. Right friends? So this upon losing water minus water, it is going to give, yes, so double bond, hydrogen, chlorine, chlorine and hydrogen. So this is alpha alpha dichloro acetaldehyde will be obtained. Up to here no confusion, right friends? So the question comes here, if I take CH3 C triple bond CH, right? So where this chlorine and hydrogen ROHCl is going to attack, so is it going to give this CH3 C chlorine hydrogen 1,1 dichloro, right? 1,1 dichloro acetone plus, yes, so it may stop at one stage also. So chloro 1 chloro acetone or alpha chloroacetone, yes friends, it is going to give 10% of this alpha chloro, and this is alpha alpha dichloro is 90%, yes friends. So how it is going to happen? Very simple, yes, it adds to 1 mole of OH Cl minus Cl plus OH minus, right? So it adds here. So what is the intermediate you will get? CH3, yes, C double bond C hydrogen, chlorine will be added here to give, this is secondary carbocation. So the concept is secondary carbocation. Now it adds to OH minus, right? OH minus to give this CH3 C OH, right friends? OH, and here double bond C hydrogen, and this is chlorine. So if it stops here, yes, it can give this compound, it can give this 10% compound, yes. However, it will not stop, it further adds to another molecule of HOCl. So here this chlorine, again where it attacks, this chlorine comes and sits here, not here, because the intermediate if comes and sits here, chlorine, so it is going to give primary carbocation, which is not favorable. So it gives CH3 COH, right? So CCl already is there, another Cl, so this is a carbocation, right friends? Plus it adds to OH minus which is there in the reaction mixture to give CH3 COH and OH, here chlorine and hydrogen, right friends? So this simply comes here and loses water minus water to give this 90% yield of the compound. This is dichloroacetone we are going to get as a major compound. This is how it is going to give these compounds. So this type of questions are very very important friends. So where this OH is going to attack, to this or this side. So in this reagent hypohaous acid, it is chlorine is going to have positive charge and OH is going to have negative charge or nucleophile. This is going to act as electrophile, right friends? This is how it gives ketones. So one alkynes gives aldehydes, whereas these remaining other alkynes are going to give ketones. This is how addition of hypohaous acid takes place. Next, diborane is B2H6. So addition of B2H6, let us take acetylene. So what is the addition compound? BH2. I can write like this, yes. So here it is a transition state where it adds to this BH2 and hydrogen like this. Syn addition of diborane takes place. Syn addition of diborane takes place where this boron is electron deficient. So electron deficient, it going to act as electron deficient. So it takes up this triple bond. So to give this syn addition compound, where this is upon reaction with hydrogen peroxide in presence of sodium hydroxide, gives enol. What is the compound? Enol. Double bond C, hydrogen and hydrogen. This is enol is nothing but here double bond ketoenol tautomerism. It is going to give aldehyde CH3 C double bond H, acetaldehyde. Acetaldehyde. It is going to give acetaldehyde. So this primary one alkyne, no doubt it is going to give acetaldehyde. So for example, even if I take propine CH3 CH S H BH2, it is going to give CH3 C hydrogen double bond C BH2. Yes. So this upon hydrolysis or peroxide oxidation NaOH, it is going to give CH3 C hydrogen, right? So C BH2 here, COH here, hydrogen will be there, right friends? So this is enol. Enol is tautomerism. Tautomerism takes place. Tautomerism takes place to give. So this is hydrogen. So aldehyde. So CH3 C hydrogen. This hydrogen comes here. Hydrogen double bond H. Propionaldehyde. This is propionaldehyde. Yes, we will get propionaldehyde. For example, if I take butane CH3 C triple bond C CH3. This is butane and do the reaction with diborane, that is BH3. So it adds to CH3 C hydrogen will be there, double bond C BH2. Yes friends. So this CH3 now upon hydrolysis H2O2 in presence of NaOH, it is going to give CH3 C hydrogen COH double bond CH3. So this upon ketoenol tautomerism gives ketone. This is hydrogen. This is COCH3. So this is ketone. What is this ketone? 2-butanone. 2-butanone is a ketone, right? So ketone we are going to get ketone. That means one alkyne gives aldehydes. So this is also one alkyne gives aldehyde, whereas other than one alkyne gives ketone. It is very, very important friends. Other than one alkynes gives ketones. However, to this compound, if I add RCO2H, that is acid, it is going to reduce. It is going to give cis compound of C double bond C. Yes, it is going to give cis-2-butene. Cis-2-butene. So BH2 will be replaced with H plus to give cis-butene. It is also very, very important friends. This reaction is very, very important friends. So diborane followed by acid, a reaction with acid gives cis-2-butene. Why? This is syn addition. It is going to use cis addition compound, that is cis alkene we are going to get. This is the reaction. Alkynes addition of diborane to alkynes, whereas primary alkyne gives aldehyde, secondary alkynes gives ketones. Right friends? Next, polymerization of alkynes. Right? So alkyne, if I take same acetylene, polymerization acetylene to give polyacetylene C double bond C double bond C. Right friends? So this is polyacetylene. This is what we are going to get, polyacetylene. It is a polymer. Yes, this polymer conducts electricity. Because it is having double bond, it conducts electricity. So it is used as conductors, plastic conductors. So as a conductor in some chips it is used, right? So polyacetylene. Next, so dimerization of acetylene. Dimerization of acetylene. What happens? C hydrogen triple bond C hydrogen plus hydrogen C triple bond C hydrogen, copper chloride and ammonium chloride. It dimerizes to hydrogen C double bond, hydrogen C triple bond CH. This is dimerization of acetylene. So this is very important reaction of these compounds, vinyl acetylene. Next very important reaction of alkenes is trimerization or preparation of benzene. So if I take CH triple bond CH, here CH triple bond CH, here CH triple bond CH, right? So red, it is very important friends, red hot tube of copper. So when I pass this acetylene through red hot copper tube at around 600 degrees centigrade, I am going to get, so this is the reaction it is going to give. So double bond, it is single bond, it is double bond, it is single bond, right? It is double bond. What is this? It is benzene. Benzene can be written like this, right? Benzene, it gives benzene. It is very important reaction friends. Benzene, acetylene, upon passing through red hot tube of copper at 600 degrees centigrade gives benzene. Very important reaction, right friends? So instead of this, if I use methyl group, same compound C, right? Triple bond, methyl here, right? C, methyl here, and C, methyl here, and triple bond C, methyl here. So what I am going to get? Same benzene, hexamethyl. So what I am going to get? Hexamethyl, same copper. I am going to use copper, red hot copper tube. I am going to get hexamethyl benzene. Hexamethyl benzene. I am going to get hexamethyl benzene. Tetramerization of alkyne gives, so CH triple bond CH, triple bond CH, triple bond CH, triple bond CH. So upon, right, polymerization or cyclization in presence of, here we are going to use nickel cyanide at just 60 degrees centigrade. I am going to get octatetraene, right friends? So these are all the double bonds is going to have. So this is how it gets cyclized and gives octatetraene. This is octatetraene. This is how tetramerization takes place, right? This is trimerization, gives benzene. Tetramerization gives octatetraene. This is how polymerization of alkynes can be explained. Ozonolysis. Let us take ozonolysis. Really speaking, ozonolysis mechanism is of alkynes is not established. However, we will get the degradation compounds. For example, if I take acetylene and do ozonolysis, ozone. So usually it doesn't require reducing agent. However, ozonolysis, if I do, I am going to get glyoxal. This is glyoxal. It comes about 10%, and remaining I am going to get this. It is going to cleave like this. So OH hydrogen, 2 moles of formic acid, 2 moles of formic acid. I am going to get 2 moles of formic acid. So this is ozonolysis, right friends? So the mechanism of alkynes is not well established. However, some mechanism shows that it forms anhydride. It forms anhydride like this, right? So anhydride of like this to give this formic acid. Hydrolysis gives anhydride, upon hydrolysis gives formic acid. If I take propyne, that is C triple bond CH, So just break here. It is going to give ozonolysis. It is going to give CH3 C double bond OH plus this side CO. So if I take another example, 2-butyne C triple bond C CH3. So ozonolysis, just break here. What happens? 2 moles of CH3 C acetic acid. 2 moles of acetic acid I am going to get. For example, if I take octane, so just simply break here. What I am going to get? COOH. Right friends? So this is ozonolysis. So two sides carboxylic acid we are going to get. Let us take another example, CH3 C triple bond C CH2 C triple bond C CH3. Wherever the triple bond you see, break here. So this side and this side, these two are same, right? So 2 moles of CH3 COOH. So CH3COH, CH3COH. Next, plus CH2 COH, CH2 CO2H, right? So this is CH2 CO2H. What is this? Malonic acid. This is acetic acid. We are going to get malonic acid and acetic acid. CH triple bond C triple bond C CH3. Right friends? So here what is happening? Just break here. What we are going to get? 3 compounds. Ozonolysis. Right? So ozonolysis of these 2 compounds, 1, 2, 3, 4, 5 carbons. So here what we are going to get? Formic acid, OH. This is formic acid, OH. Plus what we are going to get? This is acetic acid, CH3 COOH, acetic acid. Let us take one more example. Here methyl double bond CH3. So yes. So this upon ozonolysis gives what? So here double bond is there. No doubt double bond also undergoes ozonolysis. What we are going to get? Let us see. So this side acetic acid. One is CH3 COOH, acetic acid. Yes. This is a what? Let us write. C ketone CH3 COOH. This is pyruvic acid. This is pyruvic acid. This is aldehyde. We get it as aldehyde. Double bond gives aldehydes. Right? Aldehydes and ketones. So this is acetaldehyde. We are going to get acetaldehyde. This is how ozonolysis of alkynes takes place to give acids. So ozonolysis cleavage takes place to give acid. Carboxylic acids we will get. Next, oxidation of alkynes. Alkaline KMnO4. It is strongly oxidizing agent. Dear friends, Birch reagent, right, under strong alkaline conditions, so it gives carbon dioxide, this side carbon dioxide, or when it is substituted like this, it is going to give C double bond O H and R, acid. Yes friends, this is common trend. Let us take some examples and see. So based on this, let us take one compound, propyne C triple bond CH. So upon KMnO4 alkaline KMnO4, what we are going to get? Here oxidation takes place. Here we are going to get C double bond OH. So it is terminal alkyne. We are going to get carbon dioxide. It is very, very important friends. Terminal alkynes gives carbon dioxide. Let us take one more example. CH3 CH2 C triple bond C, CH2, 1, 2, 3, 4, 5, CH2 and CH3, alkaline KMnO4, right? So KMnO4, how it oxidizes? Very simple, it gives, so oxidation takes place. So this is KMnO4, it is going to give, simply break here, CH3, CH2, OH plus C, OH, CH2, CH2, CH3. So what is the mechanism? Let us take, right? So C triple bond C, if this is a compound, KMnO4, MnO4, right? O minus, KMnO4 minus. So this what happens? It takes hydrogen, it comes here, it gives here to give. This is a cyclic form, O minus Mn double bond O, right friends? These hydrogens will be there. So this cyclic ester is going to break to give dihydroxy compound. So is it going to end here? No, it is going to further oxidize to give this side hydroxylation. So OH, H, OH and H, this is OH. So this compound is going to cleave to give carboxylic acids, to give carboxylic acid when this is substituted with R, right friends? So this is how it is going to give carboxylic acid. Strong alkaline KMnO4 gives dihydroxylation, cis dihydroxylation. So that is why it going to give carboxylic acids. 3-hexane, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. 3-hexane. What is the compound I am going to get? Yes, just leave here. Propionic acid, CH3, CH2, COH. Propionic acid, 2 moles of propionic acid I am going to get. Right friends? So let us take one question. So compound A, for example, we don't know A, compound A upon alkaline KMnO4 oxidation gives isobutyric acid, plus oxalic acid plus acetic acid plus acetic acid. This is isobutyric acid, oxalic acid and acetic acid. So this is a compound. Upon alkaline KMnO4 oxidation, this is the compound we are going to get. What you have to do? Just add them. So CH3, CH3 is here, right? Hydrogen is here. C, I am going to put triple bond here. C, that is oxalic acid. C triple bond. Yes. So this side I am going to get CH3. So what is going to happen? Here, when I cleave here, I am going to get acetic acid, right? So if I cleave here, it is going to get oxalic acid, here butyric acid, right friends? So this is how you can get 3 acids. Based on the products also you can predict the starting material. Let us take one more example. For example, alkaline KMnO4, right? R ozonolysis gives 2B. A gives 2B. So what is A? If I ask, so what is A? A is, let us take CH3 triple bond C, CH3. What happens? It is going to give in 2 forms CH3 COH. Acetic acid, we are going to get 2 moles of acetic acid. This is how alkaline KMnO4 or ozonolysis we are going to get acid. So oxidation of alkynes takes place using alkaline KMnO4. This is how oxidation takes place, friends. Next, with selenium dioxide, we are going to get oxidized product. So this is selenium dioxide. So nascent oxygen using. So we are going to get glyoxal. It is very, very important, friends. Glyoxal, we are going to get glyoxal. Right? Selenium dioxide oxidizes alkynes to glyoxal. For example, acetylene to glyoxal. These are all the reactions, friends, of oxidation reactions of alkynes. Next, we will learn about properties due to CH bond. So, alkynes due to CH bond. So at the starting of this lesson, what I said, these alkynes are weakly acidic. In presence of strong bases, it gives H plus ions. Why? So we have seen that, for example, R, C, triple bond, CH. So this is sp hybridized. So what is the ratio of S here? S and P? 50% of S character gives acidity, acidic compound. So the electrons of pair of electrons, these bonded electrons will be taken up by this carbon, right, to give H plus ions. So this is how it is going to form H plus ions. So under strong base, for example, H triple bond C hydrogen in presence of sodium. Sodium is a strong base. So sodium metal, I can use H C triple bond sodium plus of hydrogen. So this is how it is going to give H plus ions, or this sodium acetylide, or I can use sodium amide. I am going to get this sodium acetylide plus ammonia. This is the compound. So if I use ammonical silver nitrate, I will get silver salt of this. So silver salt of this plus ammonia. So if I use cuprosamine, right? So this also gives copper salt plus ammonia. So it forms salts with metals. So this is very, very important, friends. So based on this, what happens if I take this sodium? So hydrogen, C, triple bond C, hydrogen. I am going to add sodium amide. So this amide takes up this proton, right? So here it comes hydrogen, C, triple bond minus plus ammonia, right? So the sodium which is there in the reaction mixture, it takes up sodium and it forms sodium acetylide, C, triple bond C, sodium. This is the sodium acetylide, right? This sodium acetylide upon reaction with, for example, if I add methyl iodide, what happens? So methyl is iodide minus methyl plus, right? So minus sodium iodide, it gives hydrogen C, triple bond C, CH3, right? Propine, we will get propine. So chain elongation can be done using this alkylation of alkynes. Chain elongation can be done using sodium amide followed by methyl iodide like this, or ethyl iodide, whatever the iodide you use, it takes up that alkyl group to give chain elongation alkynes. Right, friends? So this is how it gives chain elongation compounds. So if it is here, CH3 is here, right? So we are going to get 2-butyne. So here, if it is CH3, we are going to get 2-butyne, butene. Like that, you can prepare n number of chain elongation compounds using this metallation of this due to acidity nature of this CH bond. This is how alkynes form salts with metal amides. Next, of alkynes. Yes, what is required for Diels-Alder reaction? We require diene. Yes, so this is diene, and dienophile we require. Dienophile. So if it is dienophile, then it is alkene. We are using alkyne. In place of dienophile, we can use alkyne as dienophile. So Diels-Alder reaction can be done under thermal or light, or some Lewis acid will be used to give cyclization compound. 6-membered cyclic ring will be formed. How? It is very simple. So transition, there will be no transition state. It is going to give this cyclic compound, Diels-Alder product. For example, if I take here methyl, so what is the compound I am going to get? Diels-Alder reaction, I am going to get this methyl, or it can be prepared from this way also, right? So I can take this double bond plus, if I use this methyl, what I am going to get? Same compound I am going to get, right friends? So same compound I am going to get. For example, same this, right, plus triple bond methyl here and methyl here. You have to write like this, linear structure. You should not write like this, alkynes are linear in nature, so gives this double bond, and this is methyl, and here also methyl is here, right? It can be prepared from either of this side. So let us take methyl CH3, right, this side, plus diene, right? Can I take like this? So same compound will get Diels-Alder reaction of alkynes. So these alkynes also gives Diels-Alder reaction of alkynes. This is of alkynes. Dear friends, till now we have completed under hydrocarbons, alkanes, alkenes and alkynes. Let us see the distinguishing tests of hydrocarbons, that is aliphatic hydrocarbons, alkanes, alkenes and alkynes. Given by alkenes, and one alkynes, other than one alkynes. So what are the tests we have? Let us take Bayer's test. What is Bayer's test? Alkaline KMNO4. So it is given by alkanes. Is it so? No, it is negative. Alkanes, yes, positive. One alkynes, yes, positive. Other than one alkynes, also positive, right? Very, very important reaction, bromine in CCl4. So what happens? Alkanes are going to react with bromine in CCl4? No, negative. Alkenes, yes, positive. Alkynes, yes. Other than primary alkynes, yes. So next reaction is ammonical silver nitrate. Ammonical silver nitrate. Is it going to give by alkanes? No. Alkenes also? No. Whereas alkynes, yes, and yes. So primary alkynes and other than one alkynes also given by this. So what is the distinguishing test? It is very, very important, friends. Cuprosamide test. So this is not given by alkanes. Alkenes also not given. Primary alkynes only will give. That is, it forms salt with copper. And it is also going to give. This is, whereas other than primary alkynes are negative. This is how the distinguishing tests of alkanes, alkenes and distinguishing tests. These are distinguishing tests. So usually previously we used to do these type of tests. Bromine CCl4 test, yes, it is simple test. Bromine CCl4 or Bayer's test. However, so advanced techniques are available, though we can do these distinguishing tests, right friends? So advanced tests like NMR, IR. So IR, just by IR, yes, alkynes stretch will be there, alkene stretch will be there. So based on that you can identify these compounds. However, these are the common tests we come across in organic chemistry, that is Bayer's test, bromine CCl4, silver, ammonical silver nitrate and cuprosamide test, right friends? So this is how you can distinguish alkanes, alkenes and alkynes. I hope you understand this topic. Please subscribe my channel Venus Academy if you are not yet subscribed.